ABI, or the application binary interface, is really the contract's interface that's specified in a very standard way so that contracts can interact with each other, right? And this is really critical for contracts to interact both from outside the blockchain when a transaction is triggered targeting a destination contract, but also for messages that are sent between two or more contracts within the EVM context. So these interface functions that are specified as part of the ABI are strongly typed, and they're known at compilation time, and they're static. And what this means is that the types of the function parameters are well known at compile time, and they cannot change, because if they did, then what is specified as part of the contract call during execution will not really reflect to what the destination contract requires in terms of the function encoding or in terms of the arguments that are supplied, right? So this is something very, again, critical to how contracts function within the EVM context, and this will become clearer when we take a look at the function selector concept in the next slide. So the function selector is really what specifies the exact function within the destination contract that needs to be invoked. And the way that it is specified is by taking the function signature of the function that needs to be invoked and running that through a Ketchup256 hash, and the output that we get, the first 4 bytes of that hash are taken as the function selector. Now, how is this function signature calculated? From the function declaration. The function name is taken and it's appended with the parenthesized list of the parameter types that it accepts. Now, these parameter types are specified one after the other, with comma being the delimiter, and there are no spaces used. And this is something that is enforced as part of the ABI. This is a standard because if different contracts use different notations for function signatures, then you can imagine that when a transaction triggers a contract and sends the function selector, the receiving contract will not know which function to execute, right? So this is part of the interface between the contracts that is required, so that everyone knows what the format is, and it allows the EVM to function in a very deterministic manner. Besides the function selector, we have the function arguments that are also part of the transaction data, like we just discussed, and these are encoded as well, and these immediately follow the 4 bytes of function selector. So these function arguments start from the 5th byte onwards and go on until, or depending on the number of arguments that the particular function needs. So with this, I think we have covered a lot of the fundamental concepts that one would encounter when you start trying to understand Ethereum. So there's a lot of ground that we have covered, a lot of fundamental concepts from computer science, cryptography, decentralized distributed systems, consensus algorithms, concepts that are very specific to Ethereum like gas, EVM architecture. We have looked at the instruction set, lot of very interesting concepts. Now, the format of video presentations don't let us really get into all the details and make this into like a 10 or 20 hour long presentation. So I would really encourage those of you who are interested in diving into the details and trying to understand the nuances of many of these concepts to look at the references and go into them as much as you need and when you need. So with that, let's now step back and look at some of the higher level concepts in Ethereum, right? Some of the application level concepts, some of the approaches to Ethereum that really affect the security of Ethereum and the way that we think about, the way that we approach security, not just of smart contracts, but of the entire Ethereum ecosystem as such, and even generically or broadly, the approach to Web3 as such, right? So let's start taking a look at some of those concepts from now on. Let's talk a bit about Block Explorer. We have talked about the blockchain, we have talked about transactions, we have talked about blocks, contracts, and how they work with the various blocks in the context of the EVM or otherwise. But if we want to take a look at what has happened in the past, right, in terms of the transactions on Ethereum, the contracts that they interacted with, the application that allows us to look at all this data is what is known as a Block Explorer. It lets us explore the various blocks and their contents on the blockchain. So it's really implemented as an application, a web portal, if you will, and it gives us real-time on-chain data about all the transactions and the blocks, the gas, and everything that we really have discussed so far, right? So all this rich information is visible, is available in a very transparent manner on the blockchain, and that can be accessed via this Block Explorer application. Now, there are many popular block explorers. Different blockchains have different explorers, as you can imagine. In the case of Ethereum, we have several of them. Etherscan is one that is very, very popular. So I would really encourage you to take a look at Etherscan or any of the others listed here as well. Look at it, explore the blocks, look at the transactions, and that will really clarify a lot of the concepts that we have touched upon in the module so far. Let's talk about Mainnet now. This is a term that you will come across when you read articles about Ethereum, and this really refers to the main Ethereum network. And there is a distinction because we have the mainnet, but we also have several test nets. And these test nets are test Ethereum networks where protocol developers or smart contract developers can test their smart contracts, test their protocol upgrades, and so on. So while the mainnet uses real ether, the test nets use what are known as test ether, so that you can really simulate the gas, the transfer of value, and so on. And these test ether can be obtained from what are known as faucets. Some of the popular Ethereum testnets are Gurley, which is a proof of authority testnet that allows one to look at a lot of these concepts, test them as if they are happening on the mainnet, and this particular Gurley testnet works across all the clients, right? And it's called a proof of authority because there are a small number of nodes that are really allowed to create the blocks and validate the blocks. Then we have the Cohen testnet. This is again a proof of authority testnet specifically for those running Open Ethereum clients. We also have the Rinkeby testnet, which is a testnet specifically for the Geth clients. And finally, we have the Robston testnet, which is a proof of work testnet, unlike all the other proof of authority testnets. And this being a proof of work testnet means that this is really the best representation of mainnet Ethereum, which also uses proof of work. So a lot of the mainnet simulations can be done very accurately or very close to how it would behave on the mainnet by running it on Dropster. Now these testnets are also evolving. New ones are being added over time, over the years, trying to make it as easy as possible for the developers to simulate the real mainnet Ethereum blockchain and all its dependencies. And this again becomes very critical to security, because in security, testing is something very fundamental. And if you do not test, or if the testing environment is not accurate, not very similar to the production environment, then the assumptions, the dependencies and other aspects that are tested will be very different from what happens when you deploy the contract. And this could really cause a lot of security issues, as you can imagine. A term that you will come across in Ethereum literature very frequently is EIP. This stands for the Ethereum Improvement Proposal, and as it is named, these are proposals put forward by researchers, developers, community members in the Ethereum ecosystem to make changes to different aspects of the Ethereum protocol. And there's a specific process, very well defined process for EIP, from the time somebody proposes to the way it is discussed, debated, voted upon, and finally make it into a standard or a specification. And depending on the different layers or aspects of protocol of Ethereum, the proposal targets, these could be either addressing the core aspects of the protocol, the networking aspects, the interface, or some of the token standards. And ERC is something you'll come across repeatedly, even in this module, in the forthcoming modules. ERC stands for Ethereum Request for Comments, and this has sort of become the used term for token standards, right? So you would have seen, or we'll talk about ERC20 token standard, ERC721 token standard, and so on. And these are really being created as part of the EIP process. And there are also some meta and informational EIPs that don't address the protocol as such, but that address some of the governance aspects of this whole ecosystem, the process, and so on, and also address some of the informational aspects of how these standards and specifications are written and distributed within the community. Let's now talk a bit about ETH 2.0. This is really a short form for Ethereum 2.0, and a topic that you wouldn't have missed if you have looked up any of the media articles, research articles written about Ethereum in the past few months or even a year. Now let's get one thing out of the way. So Ethereum 2.0 is really a set of interconnected upgrades to the existing Ethereum that's being made. And the reason why it has been referred to as ETH 2.0 is because this is perhaps the biggest set of upgrades that are being made to the Ethereum protocol since it started several years ago. Right? So this is not a separate version of the protocol or a separate thing that is very different and very separated from the existing Ethereum protocol. It's really a continuation of all the research and development activity that has happened on the protocol. The 2.0 really sets aside or signifies the fact that this has some of the biggest upgrades, and those upgrades are really across three vectors: scalability, security, and sustainability. So these upgrades to Ethereum 2.0 are going to make it much more scalable than the protocol that we have been using so far. And this is going to be made possible by the concept of sharding. We won't get into details of these concepts, but I would really encourage you to see all the fantastic literature that the Ethereum R&D teams have put forth on these topics. Then there is the more security aspect, and this is really the transition from the proof of work to a proof of stake for the protocol that we touched upon when we discussed proof of work earlier on in this module. Right? So this is again a huge change to how the protocol functions, and it offers immense economic security benefits compared to the proof of work that we have been using ever since Ethereum started. And there's a related concept of sustainability. So with proof of work, as we saw, there's a certain amount of computation that has to be done to pass the difficulty level, right? This is really for Sybil resistance, part of the consensus protocol. So there is computation that is done, and as a result, there is real energy in terms of running the mining nodes that is consumed. So this goes away to a great extent when we transition to proof of stake, and that makes, or that is going to make, Ethereum much more sustainable, much more green when it comes to environmental impact and things like that. Right? So this is really the set of upgrades that the Ethereum community has been working towards and is going to happen as we speak. It's already started happening with the deployment of the beacon chain and so on. So the set of changes are really going to accelerate in the coming months and years. Now let's zoom out a bit again and discuss some high-level properties of Ethereum or Web3 in general that affect the security mindset for the space, or the security approach that is very different from the Web2 approach, if you have seen that or if you're coming from that domain. And the first of those concepts is that of immutability, right? Immutable code. We talked about this in the context of the blockchain being immutable because of all the blocks being linked with hashes, and the proof of work and what it requires for somebody to go back in time and change one of the blocks or any of its contents. And that really contributes to the economic security and the immutability aspect of the blockchain. But when it comes to code, the contracts that are deployed on the Ethereum blockchain, those are considered, or those are designed in a way to be immutable as well. Right? So what this means is that once a contract's code is deployed, it is technically considered immutable. That means that it cannot be changed, at least in theory. There are some exceptions we'll talk about below. So it can theoretically, well, it can practically be done, but from a design perspective, from an ethos perspective, this is not desirable, right, in this space. And you can imagine how this immutability of code really affects the security aspect, right? With software in the Web2 space, and in general, we know that software will have bugs. One really cannot prove the absence of bugs or the absence of vulnerabilities, errors in the software. And immutability affects this to a great extent, right? So if we have bugs, we know that bugs will exist, and if we cannot change the contracts, then how do we fix it, right? How do we fix that code and redeploy the fixed code as we've been used to in the Web2 world, where we keep getting updates to the operating system or to the different apps continuously to fix bugs, optimizations, and so on, right? So this is something very fundamental to the Ethereum or to the Web3 space that we have to keep in mind. But there are practical exceptions, right? The deployed contract can be modified, the functionality can be modified, and this can be done in three ways. The contract can be modified and redeployed at a new address, but then you would have to carry over all the state, and all the users interacting would have to migrate to interacting with the new address. But this is typically considered impractical, but it can theoretically be done. The modified contract after, let's say, the bug fix or a version 2 can also be redeployed as a new implementation of what is known as a proxy pattern. And this is something we'll see in the forthcoming modules when we learn about Solidity and so on. The proxy pattern, the proxy contract points to an implementation contract, and that implementation can be modified, right? Can be upgraded. And this is really the most commonly used approach to contract upgrading. And this has huge security applications if it is not done right, if it is not done in a trustworthy manner, if there are certain best practices that are not followed, and so on. The final way of upgrading a contract for whatever reason is by using the create to opcode. We talked about this. This opcode really allows updating a contract in place at the same address using the same init code that was used to initialize the contract. Again, the details are many, and a lot of it is something that we haven't discussed. We will touch upon this in the forthcoming modules, but at a high level, the concept of immutability that is so fundamental to this space really has a huge impact to how we think about security and how we actually can implement security in this space. Now let's step back again and revisit the concept of Web3, the vision for Web3, the motivating factors for all the teams that are building on Ethereum, that are building Ethereum itself, the protocol, or any of the other blockchains in the space. Web3, the idea is for it to be a permissionless, trust minimized, and censorship resistant network for transfer of not only information but also value. Now this vision is what really drives Web3, and this has implications to the underlying architecture, and we talked about this from a peer-to-peer context, which is very different from the client-server paradigm of the Web2 context, where the peer-to-peer applies not only to compute but also to storage and network. And in the case of Ethereum, it's really the triad of Ethereum, Swarm, and Waku that are addressing the peer-to-peer components at an architectural level. Privacy and anonymity are again very big motivating factors in Web3, and that really have a huge implication on how we think about security in this space and how we can actually conceive implementing various security measures in this space. But it's not completely a fresh start. There are a lot of Web2 security principles, best practices, software engineering best practices that have been researched, experimented, developed, and refined over the last 3 or 4 decades that still apply very much to Web3. But having said that, there are still many aspects of Web3 security which are really a paradigm shift, and we'll talk about why this is and what are those shifts that can be thought of as something very unique to the Web3 security space. The first aspect is that of languages, and languages are really critical because that is really how projects really implement their ideas, deploy it, and let users interface with it. So this is really fundamental to the security of any product, any architecture, if you will. So in the case of Web2, there have been numerous programming languages, right? Really tens or hundreds, and some of them are way more popular than the rest. Started with C, C++, during the Unix days, 30, 40 years ago. And since then, we have seen different declarative languages, object-oriented languages, scripting languages. Some of the most popular ones have been JavaScript, and more recently Go, Rust, and even some unique languages such as NIM that have been used to implement Ethereum 2 clients recently. All these languages are still applicable to the Web3 space, right? Because Web3, as we discussed, is really a combination of smart contracts that run on the blockchain, but there's also a web component, the interface component, which is really how users interact with the contracts on the blockchain. So when it comes to the web aspect, all the Web2 languages are still very relevant. A lot of them are popular even here in terms of the interface, but also in terms of the tooling that is used for the development of smart contracts themselves. Now, smart contracts themselves have a special language, right? And in the case of Ethereum, that's Solidity. Solidity is the most widely used language for writing smart contracts on Ethereum. Now, there are others that are work in progress. Some of them, like Viper, are gaining traction, but for the majority of the smart contracts that we see deployed, Solidity is that language. And all these languages, the smart contract languages, were created specifically for Web3 and specifically for Ethereum in this case, right? So those and the security features of those languages have huge implications to the security of the smart contracts and the applications that are built on top of it, as you can imagine. The other concept that is very unique to Web3 is the differentiation between on-chain and off-chain. So here, chain really refers to the blockchain, and on-chain means something that is running or executing on the blockchain or within the blockchain's execution environment. Off-chain is something that is running, executing off or outside the blockchain. So in the Web2 space, everything is off-chain because obviously there is no concept of blockchain in the Web2 space. But in the Web3 space, there is an off-chain component combined with an on-chain component. The off-chain component is really all the Web2 or the glue that binds the web interface to the smart contracts that are running on-chain. So that distinction is really critical when we think about security. So the security of Web3 is or has to think about the security implications of anything running or interacting off-chain with that running on-chain as well. So it's not just smart contract security, but it's also the security of the off-chain web or mobile app components that interface with the on-chain components, that is the smart contracts. So the main difference, however, between Web2 and Web3 security is the on-chain component, the smart contracts. So when it comes to thinking about security in a different way, it's not just the Web2 or the off-chain component, but the smart contracts that are unique and specific to Web3. That is something that is very new from a security perspective that we need to think about, we need to design, look at the pitfalls that are unique to smart contracts, look at the best practices, and so on. The other big aspect that affects security of everything that is done in the Web3 space is the ethos or the design approach towards everything here being open source and transparent. Now, we have known open source in the Web2 world for several decades, so that's not very new, but from a approach perspective in the Web2 space, we do see most of the products or many of the products being proprietary products from a licensing perspective, from a source code availability perspective, things like that. But in the Web3 space, the design or the ethos is that all components are expected to be open source by default. And this really stems from the permissionless aspect, the trust minimization aspect, the censorship resistance aspect that we talked about. So that has huge implications to security. Now, in the context of smart contracts, the contracts are again expected to be open sourced. They're also expected to be verified contracts. In this case, it means that the bytecode of the contracts deployed on the blockchain are expected to be source code verified using one of the services that provides this service, such as ethos can. And this really means that the source code of the contract is the same one that was compiled and deployed as the bytecode of the contract that users interact with. Right? So that verification is something critical and something expected by default in this space. And everything that happens in the blockchain is transparent, right? All the transactions that are interacting with the contract or transferring value between EOAs, they're all part of the blocks that can be explored as part of the blockchain using block explorers. The state of the various contract accounts is again public, and all this is real time, right? Nothing is hidden behind paywalls or provided on a need basis. So it's all out there. Anyone can actually run an Ethereum node so that you don't even have to rely on a block explorer or any service like that. You can look at transactions as they happen in real time on the blockchain. You can also look at transactions that are waiting to get into the blockchain. There are what are known as mempool explorers by some of these services that provide this capability. One can even do that by running an Ethereum node themselves. So in effect, there is really no security by obscurity, by design, right? That's the ultimate goal and ethos of this space. And this has a tremendous impact on all security aspects, the design aspect, the architectural aspect, the operations aspect of security, and so on. The other related concept is that of the applications and the infrastructure being unstoppable and immutable. We talked about dApps and how they run on a decentralized infrastructure. The goal is, even for the governance of these protocols and infrastructure, to be decentralized. So what this means is that there is no single entity that can unilaterally decide to make changes, to start something, to stop the application, be it a dApp, be it the protocol, be it the surrounding infrastructure, or the governance itself. And specifically in the case of smart contracts, there shouldn't be a single entity, and this could be the project team itself that has built out this application, that has built out these contracts. They shouldn't be unilaterally be allowed to change, stop, and withdraw funds, things like that. And this really stems from the trust minimization motivation, the censorship resistance aspect, and so on. Right? So they're all very interconnected aspects, and as you can imagine, they have huge implications to when it comes to upgrading the contracts, when it comes to fixing the bugs, when it comes to really doing anything with the smart contracts once they're deployed, because they are expected in theory and by motivation to be unstoppable and immutable. So from a security perspective, this makes it really hard to ship the software, because once you ship it, once you deploy it, if there are any vulnerabilities found, it's very hard to fix it. It's very hard to do an instant response which is something that we take for granted in the Web2 world, where we get software updates even without our knowledge to the operating system or to the various apps on our phone and so on. So in the case of Web3, in the case of Ethereum, smart contracts, this has huge implications to how we think about design and really operationalize security. Now, this is really the ultimate goal. In practice, as we go through different stages of progressive decentralization, these things are evolving. So the best practice right now is to do something known as a guarded launch. We'll talk about it in the future modules. But for now, the best practice is to really have the ability to make changes, to upgrade the contracts, to have an emergency withdraw function to remove the tokens in case there is an emergency, right? So that is really sort of the stopgap measure as we progress towards complete decentralization. Once we have enough confidence that the contracts are running and there are really no bugs, vulnerabilities or exploits, then a lot of these things are disabled in the code. The kill switches or the upgradability aspects, the governance, all these things are in a progressive manner made more decentralized over time. Right? So this is something very critical when it comes to thinking about security in this space, when it comes to implementing security in this space, be it in the software engineering practices, be it in some of the monitoring tools or incident response and so on. So we've talked quite a bit about the technical aspects so far. Now let's switch gears and talk a bit about, while so far we have focused mostly on the technical aspects, let's take a look at the people or social aspects that are as critical, if not more, than the technical aspects. And this is because it's really ultimately people who are behind the projects, who are developing it, who are operationalizing it, who are maintaining it, who are governing it. So a lot of the things from the Web2 space that we are used to when it comes to regulatory aspect, when it comes to legal aspects of who is responsible, what are they responsible for if something goes wrong, change dramatically when it comes to the Web3 space. One of the things is the pseudonymity, or who is the team behind a particular project. So there is a trend, an increasing trend towards some of the teams, some of the people involved in the projects being pseudonymous, and this could be because of the regulatory uncertainty regarding cryptocurrencies or crypto space in general. It could also be because of the legal implications thereof, and this changes the way we think about reputation, the way we think about trustworthiness when it comes to applications, projects, or products. This also affects the legal or social accountability when it comes to projects. Who is responsible? Who is accountable? If the team is pseudonymous, how do you even know what they're doing with the project, with the governance, and so on? There is this concept of trusting software and not wetware. Wetware, in the sense, people. That is great, but there are still social processes where people are involved to a great extent around building the project, around rolling it out, around the governance of the projects, that has a huge implication towards the security posture. So these are the non-technical aspects that have a huge impact on the way we think about security in the Web3 space in general. Then there is also the concept of DAOs, DAO, decentralized autonomous organizations. These really stem from the trust minimization aspect of, or the censorship resistance aspect of Web3, Ethereum also in this space. And this is to really minimize the role and the influence of centralized parties or a few privileged individuals in the life cycle of the projects. And what this means is that the project ultimately evolves or aspires to be governed by a DAO. And this DAO can be comprised of a community of token holders for that particular project, and they make voting-based decisions on how the project treasury should be spent, what the protocol changes should be, and in some of the cases, all these are decided on-chain and affected on-chain as well. So while this reduces the centralized points of wetware failure, as we call it, it also slows down decision making on a lot of the security critical aspects. I mean, imagine if there were a vulnerability to be found in a deployed contract and somebody had to create a fix and deploy the fix. And if that had to go through a DAO for the decision making, you would have to give a certain amount of time, a certain window of time for the token holders to vote and for that decision to be taken. So this is a trade-off. I mean, a centralized party entity in the Web2 space can make this decision immediately, unilaterally, and deploy that fix in a few hours, if not less. But in the case of Web3, in the case of the DAOs, the decision making is decentralized, but it has downsides or it has implications from a security perspective. Now let's switch back to the technical aspect and take a look at the entire technical stack and the implications of that on security. So if we look and think about the Web2 aspect here and then contrast it later with Web3, Web2, going all the way back to the advent of internet 40-50 years ago, the various protocols that were developed as part of the TCP/IP stack, some of the competing ones, the way they were standardized, then the advent of the World Wide Web that really launched the Web 1 to the world, the concept of browsers, the concept of web applications, the client-server paradigm, all this happened in the last 30, 40, 50 years. And then came the Web 2.0. This is where the enterprises, be it IBM, Microsoft, the introduction of Linux to the world, various hardware architectures, various operating systems, the dominance of Microsoft, Apple, and more lately Facebook, Amazon, and the likes. All these have contributed immensely to the development and the maturity of the Web2 ecosystem over the last 40-50 years. And this has huge implications to the security in that ecosystem as well, that has developed in tandem with all those technologies, again, over the last 30-40 years, be it the firewalls, antiviruses, intrusion detection systems, intrusion prevention systems, various kinds of security systems for email, for the World Wide Web, for your personal laptops on the server side. All these hasn't happened overnight. It's not happened over 2-3 years, but has really happened over decades. And they've evolved with time as well. They've evolved with the technology stack, with the various languages, with the various systems, the new use cases, and so on. And more lately, if you think about the entire ecosystem of smartphones, the apps around it, the advent of the iPhone, Android, they didn't exist 15 years ago, right? And they entirely changed the way applications are built, the apps are built, the way they are deployed, the way they are distributed, the security of those apps, the containerization within those mobile OSs, all these have happened in the last 15, 20, 40 years. Now contrast that with Ethereum, with Web3 in general, but specifically Ethereum. Ethereum itself is not more than 6 to 8 years old. Brand new protocol that got inspired from Bitcoin, and Bitcoin itself is not more than 12 or 13 years old, right? So this entire ecosystem, and specifically the technical stack of Ethereum, starting from the protocol, going to the virtual machine, EVM, which is a very simple stack-based machine. Again, taken a lot of inspiration from some simple architectures from the Web2 space, but has some very unique properties like that of 256-bit words, or more specifically, more uniquely, the associated gas semantics, which has no parallel in the Web2 world. All this is very new. Now, if you look at the languages that are used to write smart contracts, again, something very unique to Ethereum, very unique to Web3, there are a handful of them. There's Solidity, which is by far the most widely used smart contract language. There's Viper, that is used by a couple or more of some popular projects. And there are a handful of others that are being researched upon. And then if you look at the developer tool chain, that is really critical to building, deploying, monitoring applications on Ethereum, Hardhat, Truffle, Brownie, OpenZeppelin libraries, all these are barely 3 to 4 years old, right? So compare that, it's an order of magnitude of difference between the Web2 world and the Web3 world. 30 to 40 years versus 3 to 4 years. And very specifically, if you look at the security tools like Slither from Trail of Bits, Mythex from Consensus Diligence, and some of the others from OpenZeppelin and other companies in the space, they're fantastic tools, but they've been around for not more than 4 or 5 years, right? So that test of time, or the evolution of these tools, adaptation of these tools to differing use cases, differing protocols in this space, differing needs, is very critical when you start thinking about implications to security. And all these are not happening in a very coordinated, very tandem manner. They're all happening in different timelines by different teams around the world, often not very coordinated. Right? So all these are moving pieces, and there are several such layers. And this technical aspect, but from a very process oriented way, from an ecosystem perspective, has huge implications to the way that security is thought about, is worked on, is deployed, that is often missed in this space. Now let's look at the threat model, which is really very central to how security is thought about, is really critical to how security is designed. Web3 is all about what is known as the Byzantine threat model. I would encourage you to go and look at the Byzantine generals problem, which is somewhat fundamental to the space. That will give you a better understanding and appreciation for the security trust or threat models that we really work with in Web3. Let's step back and look at the Web2 space. Right? Web2 has very defined concepts of trusted insiders and untrusted outsiders. Right? And some of this has changed over the years because there is obviously a huge aspect of insider threat that has been recognized in the Web2 system as well. But if you look at the products and the evolution of some of these products in the Web2 security space, be it antiviruses or firewalls or any of the network security, perimeter security devices and applications, there is still an aspect of insiders and outsiders. Right? And this goes away to a great extent, if not completely, with Web3, because Web3, the threat model is really all about Byzantine fault tolerance. And this really means that anyone, including the users, could become the abusers of that system. And this is done or can be done in a very arbitrary, malicious way. And this is really governed by the crypto economics, or what is really known as mechanism design. Right? So this again has really big implications to how security is designed and deployed, because you have arbitrarily malicious adversaries that are really motivated by mechanism design. And these adversaries, they could be users, they could be intermediaries, they could be people who are thought of as being critical to the ecosystem, and they could include anyone. It could be developers, it could be miners, validators, infrastructure providers, and users. All of them could potentially be adversaries. This fundamental difference in threat model between the Web 2 and Web 3 is what drives and what makes the Web 3 security aspects really challenging. And this is really the underpinning of Web 3 being untrusted by default, where the users could become the abusers, and Web 3 being really the ultimate zero trust scenario. Let's now talk about keys and tokens. Again, to compare and contrast some of these terminologies and aspects that are very specific to Web 3 and how they differ from the Web 2 world. Keys and tokens are very commonly used in terminology as well as the implementations of various protocols in the Web 3 space. And these are the private keys that we talked about that control the EOAs in Ethereum. This really is all about the public key cryptography that is used fundamentally in the Web 3, specifically in Ethereum. Cryptographic keys are really first-class members of the Web 3 world. And as much as we unknowingly use cryptography in the Web 2 world, Web 3 is really taking this to everyone, because the whole point is for the people, for the end users, to take control of their assets, of their tokens, with keys that are in their control. Because remember, there is no centralized entity that is responsible for it. At least aspirationally, the goal is for there to be no centralized intermediaries that can sit between you and your access credentials, your keys, or your assets, that is your tokens. Now let's contrast keys with passwords that have become synonymous with the security, or what is wrong with security in the Web 2 world for several decades now. Passwords, all of us have tens or hundreds of them, most of them very simple, reused, and very few of the users really use password managers, but they rely on passwords being reset or changing them when they are lost by the entity that actually controls access to to the website or to any service that is using these passwords, right? So that ideology or of passwords is intentionally by design absent in the Web 3 world. At least aspirationally absent in the Web 3 world. That's the goal, that's the future that Web 3 applications are headed towards. And this is really enabled by the use of keys that are expected to be always under the control of the end user. So unlike we have the resets or the restores of passwords, loss of keys or loss of the seed or secret phrases that generate these keys is really irreversible, and there is no recourse or entity that you can go to and have them restored. At least that is the goal. So this is a significant shift in the security mindset coming from the Web 2 world. where passwords again are ubiquitous, and we see the problems with passwords being reused, despite the use of 2FAs, despite password databases being dumped, and the various password replacing technologies such as biometrics still very slowly picking up adoption in this space. So that is that sort of sets the ground for again a comparison contrast between the Web 2 and the Web 3 world. And a similar situation exists with tokens and their data equivalent in the Web 2 world. So in the Web 2 world, the data that we have on the various services, on the various websites, or even the financial assets, the financial data, if something happens to it, if it is stolen in some fashion, the worst thing that can happen is that the private personal data is maybe sold in the dark web and used to create accounts on your behalf or take loans or something like that for some monetary gain. And this has been getting much harder. It takes a certain bit of effort on on the attacker's side. It's also getting much harder because of the various checks and measures. Some of these are technical, some of these are regulatory that are being put in place. With all that, the Web 2 security space, the implications of any data loss is indirect, takes time and effort from the attacker's perspective, and in some cases, because of regulations or because of centralized entities, can also be reversed. Right, the impact can be reversed. Now let's contrast that with tokens that are used in the Web 3 space. Tokens used as protocols, used with by protocols, or let's take the example of Ether or any of the cryptocurrencies. If those tokens are taken away from the account, from the account that you control with your private key, then there's really no recourse unless these tokens happen to be in centralized crypto exchanges or in the control of some other centralized parties that take the responsibility for any loss of such tokens. The end user typically ends up losing these tokens irreversibly. Right? And these are again interrelated to the immutability aspects, to the trust minimization aspects of this whole space. But that again is a contrast between the fines, regulations, the possible reversals of some of these impacts in the Web 2 world versus the irreversible or immutable aspects of the Web 3 world. So these are again very critical things, not very technical, but technical implications that have huge ramifications to how security is thought about and designed and conceptualized and acted upon in the Web 3 world. Let's now talk about composability. Composability really means designing components, designing applications in a very modular way so that other modules, other applications can interface with them to increase the utility that is got from either of the two components, right? And this has to be done in a way that is very easy, that is very permissionless, without a lot of work and effort required. Again, going back to the Web 2 space, a lot of the work that has happened, a lot of the applications that are built by the various enterprises for various reasons, really to protect their business interests, are designed in a way such that they work really well within their ecosystem or their suite of products. And they're not really meant to be very composable, very interactive with other applications or other components from other entities, from other vendors, potentially their competitors. However, in the Web3 world, the aspirational goal is that of borderless, permissionless innovation and censorship resistance. We have talked about this repeatedly. And this really inspires all the applications, smart contracts or any other off-chain components to be open and composable by design. And what this means is that anybody, any user, any part of the world can deploy applications, can interact with it, be it contracts, be it any other component, has to be composable. That is really the aspirational goal, and that is what drives innovation in this space. Now, this is great. This composability is fantastic and has really resulted in very accelerated innovation and compressed timescales we'll talk about in the next slide. But this again has implications to how security is thought of and what is practically possible with security in this space. So when you have this unconstrained composability where any smart contract, any application that is deployed can really be acted upon, can really be combined or connected with any other smart contract on the chain, then it leads to sort of an explosion of the dependencies, of the configurations that are possible, of really all the components that are part of this entire system. And this makes characterizing Web3 vulnerabilities and exploit scenarios very challenging because it requires really a very deep knowledge of all these interacting composable components along with their very different constraints that could change because of composability and their configurations that could be affected by interactions with other components. So this complexity is something that we'll appreciate once we start looking at smart contracts and some of the very popular applications of smart contracts in this space and how they work with really any other smart contract in a very composable way. So this again is something to be thought of because it has serious security implications. Now we talked about timescales, right? And we've discussed the Web2 timescales where over decades innovation has happened with the internet, with the World Wide Web, with the Web 1, Web 2.0. And a lot of this has happened in different parts of the world in somewhat isolated manner, at least the very initial stages within government research organizations and then academia, universities, a lot of them in the western part of the world, and then moving on to enterprises, corporates driving a lot of this research. But a lot of this is again for mainly for the interests of business and to sort of have a monopoly over the business interests. A lot of this has happened within walled gardens, as they're called, right? Because of this, the time scale of innovation, although it seems really fast, exponential in some ways, smartphones, 15 years, PCs, Moore's law, all that good stuff, those time scales are really long when you compare that to the compressed time scales of innovation that happen in the Web3 world, and specifically Ethereum. And this is again really driven by a lot of these interrelated concepts we have talked about. Everything being open source by design, being composable, being permissionless, borderless, really no walled gardens, and combine that with the mechanism design, where a lot of this is incentivized by tokenomics, right? And the execution speed is really accelerated because of all these reasons. And as a side effect, unfortunately, security has, in some sense, taken a backseat. It hasn't been really thought of as much as it should be in the design of some of these applications, in the development of a lot of these smart contracts. And this has really what contributed to a lot of the vulnerabilities we have seen within smart contracts or the Web3 applications, and has led to exploits which have lost millions or tens of millions of dollars overnight in a fraction of a second, in a few transactions. And this is all, remember, it's all irreversible. There is no centralized third party, right? So all these aspects of pseudonymous teams in some cases, the Byzantine threat model, the use of keys, the use of tokens, the lack of any centralized third party that can reverse the negative side effects of some of these exploits, all these interrelated concepts really affect the security aspects of Ethereum and Web3 in general. Test in prod. While this may have started as a meme, there is certainly an element of truth to it in the Web3 space and Ethereum. Now, if you go back to the concepts of compressed timescales that we talked about, unrestricted composability of contracts and applications in this space, the Byzantine threat model, and really the challenges of replicating the full state of a live blockchain in a test setting, all these are really what make testing in a testing environment very hard. Unlike a Web2 world where there are very clear distinctions between a test environment and a production setting for various reasons of owning the complete stack, the maturity of the tools, the lack of sort of unconstrained composability with arbitrary components outside of the stack for that particular product. So all those aspects that are very well defined in the Web2 space from a testing perspective and what really gets deployed to a production setting, those aspects are very challenging in the Web3 space. And this is further complicated by the tools or the maturity of the tools that are still experimental in some sense in the Web3 space, and also the mechanism design aspect of it, right? Of the attackers and the users potentially being the abusers, all those aspects we talked about. All these things come together to make testing, which is really fundamental to thinking about security and making something more secure or getting a better level of assurance from the product, they make testing very hard to do because the real world failure models can not be replicated very easily in a test environment. And what this implies is that it forces quote unquote realistic testing to happen only in production in the case of Web3, in the case of Ethereum. And this is really on the mainnet. So none of the testnets, we talked about the testnets, are really giving the capabilities to the developers and the project teams to really test as well as they can to match some of the assumptions and constraints that their software contracts will see on the mainnet. And this implies that the really complex technical exploits, crypto-economic exploits, can only be discoverable upon production deployment on the mainnet. This is again a hypothesis, but it is worth thinking about. The Web2 space has a concept of SSDLC, which stands for Secure Software Development Lifecycle. There are many approaches to this. There are many different processes and ways to go about it. But in general, any Web2 product, software product, hardware product, or service generally has a version of SSDLC which is used during the development lifecycle. And this really guarantees that some minimum requirements have been met in a combination of testing, internal validation, some sort of external assessment, depending on the product, where it could be a product audit, a process audit, maybe even penetration testing if it is applicable to that product. And also, depending on the nature of assets that are managed, the risk that is faced, the threat model that is anticipated, and even the specific sector or domain that the products are introduced in, such as, let's say, the financial sector. All these also have certifications that the product, application, or service has to meet, right? So this is really prevalent in the Web2 space, has evolved again over the last several decades. But when it comes to the Web3 space, we do not see a mature SSDLC yet. What we see is this concept of audits. And unfortunately, the life cycle of development has really boiled down to building the product, be it a smart contract or a Web3 application, building it, getting an audit done from an external company, a security firm that specializes in, let's say, smart contract security, and then going ahead and launching it. And there is an expectation both from the development team as well as the users, the market in general, to view or perceive this audit as really a silver bullet, something that detects all the security issues in the product, in the smart contract, fixes everything, and then is really sort of guaranteed to have no bugs, no vulnerabilities in the product when it is launched. This is unfortunately what we see today, something that's really bad in the ecosystem and needs to be fixed. Continuing on to the use of audits and the perception around audits, it is unfortunately seen as sort of a stamp of security approval from a third-party security firm that specializes in these audits. And there are various reasons to this. Again, all the factors that we talked about, the compressed timescales, the evolving tool chain, all these moving pieces. But there are some fundamental aspects that contribute to audits being perceived in this fashion. At least this is the hypothesis and my opinion. The big one is, in general, the lack of in-house security expertise. Now, given the rapid innovation timescales in this space, the developers are few, and there is a huge demand for developers, and there is a bigger demand for people who not only understand how to develop in Ethereum and the Web3 space, but who understand the security pitfalls, which really requires a greater level of effort, greater level of expertise, if you will. And this lack of in-house security expertise and really the challenge of wanting and having to launch some of these protocols as fast as the team can really do, forces such teams to seek out external audit firms and get these audits and think of them and market them and brand them as stamps of security approval. So there's this very unrealistic expectation from very unreal expectations from these audits that they're a be-all, catch-all for all the security vulnerabilities, all the security bugs that are anticipated in that smart contract or in that Web3 application. And for reasons of great demand and very low supply of this expertise, these audits are also very expensive. There are very few audit firms compared to the demand. And this is sort of what leads to a vicious loop where projects want audits, but all the audit firms are really booked 6 months, 9 months, depending on the market conditions. And this really is sort of a core problem in this space. And this is really what this module is about, is this bootcamp is about, is to talk, learn collectively about Ethereum in this module, but in the forthcoming modules, talk about Solidity, talk about the security pitfalls, talk about the audit aspects in the space, so that we increase this pool of talented auditors. So this brings us to the end of the first module for this bootcamp. We covered a lot of ground with respect to Ethereum 101. We touched upon 101 key topics in the Ethereum space. We looked at what a blockchain is, how is Ethereum different, all the various concepts of addresses, keys, blocks, transactions. We dived into the EVM, the virtual machine. We looked at the instruction set. Then we stepped back and took sort of a 10,000 foot view of how all these aspects of Ethereum affect the high level security mindset, design, principles of the space. So hopefully you have a better idea of what Ethereum is after going through this video for this module. Again, the expectations, just to level set that, these are very complicated topics. There are a lot of details, many nuances, a lot of which we haven't touched upon in these 101 slides of this module. So I would really encourage you to take a deeper look at the references on a need basis, as much as you can, as much time as you have, so that you get a firmer, better understanding of all these deeper concepts and nuances.